Online design and simulation of the Semtech TS30012 DC switching regulator circuit. TINA and TINACloud allows fast and accurate simulation and design of power management integrated circuits both offline and online. In this video, we will demonstrate the online design and simulation of the Semtech TS30012 DC synchronous switching regulator evaluation circuit using TINACloud. Startup transient simulation. The startup transient of a DC converter is the period of time during which the converter is transitioning from its off state to its steady state operating condition. In most simulators, the startup transient simulation takes a long time, since the whole process from the initial state to steady state is simulated. However, due to the built-in average model in TINA and TINACloud, the simulation takes only seconds both online and offline. TINA and TINACloud can also be used to perform switching mode transient analysis. Due to the advanced multi-core solvers in both software, switching mode transient analysis is still quite fast and results in more detailed waveforms. In addition, TINA and TINACloud include a very fast calculation of the ripple voltages using the combination of the average and switching models. Let's load the TS30012 evaluation circuit in TINACloud. For running transient analysis, select Transient from the Analysis menu. Note that by default the Use Switching Model checkbox is not checked. This means that the fast average model is used. By pressing the Run button, the time function of startup transient appears within a few seconds. If you click on the top right of the startup diagram and run a cursor on it, you can check that the output voltage is 1.2 volt. Redesigning the circuit. TINA and TINACloud's design tool can determine circuit parameters to achieve a predefined target output. To use the design tool, select Redesign this circuit from the Tools menu, or double-click the text box on the left side of the current circuit. The design dialog appears. So far the V-out voltage has been 1.2 volt. Let's redesign the circuit to generate a 3.3 volt output voltage. To do this, change V-out to 3.3 and press Run. The following screen appears. The design tool changed the RTOP resistance to 26.7K and displayed a quick diagram of all the relevant analysis results based on analytic calculations. If you click on the top right of the startup diagram and run a cursor on it, you can check that the output voltage is now indeed 3.3 volt. You can also run a more accurate numerical transient simulation on the redesigned circuit and see that it provides nearly the same result as the analytic result. Finally, you can also run the switching model if you check the Use Switching Model checkbox at the Run Transient Analysis dialog. The calculation takes 3 minutes, and the V-out voltage is very similar to the V-out curve provided by the average method. Let's select the output voltage. The only difference is in the ripple, which is not provided by the average model. However, both TINA and TINACloud include a fast and accurate method to calculate the ripple voltages in steady-state analysis. Steady-state analysis. Steady-state analysis of a DC power supply is the analysis of the circuit's behavior when it has reached a steady state. This means that the output voltage is constant, except for the ripple voltage, and all the components in the circuit are operating in their steady-state conditions. TINA and TINACloud provide a very fast and accurate method for determining the ripple voltages in any circuit. They use built-in average models to quickly reach the steady state, and then switching models to determine the ripple voltage. This method allows a very fast determination of ripple voltages for any circuit settings, without the need of storing initial values of inductors and capacitors in the circuits. To demonstrate how this method works, let's load the following circuit. This circuit is identical with the previous circuit, except for some global parameter settings. The global parameter settings determine the starting time, 5.5 milliseconds, of the switching mode transient analysis. We will use TINACloud to analyze the circuit and determine the ripple voltage. Let's run transient analysis. After a short calculation time, the ripple voltages and current of the outputs appear in a diagram. Similarly, you can also quickly simulate line stepping and load stepping circuit response. Line stepping analysis. Line stepping analysis of DC-DC converters is used to determine how a DC-DC converter responds to changes in the input voltage. TINA and TINACloud can simulate the circuit response extremely fast due to their built-in average models. Load the following circuit. To see how the circuit responds to a step change in the VCC voltage, run transient analysis. In a few seconds, the circuit response will appear in a diagram. Load step analysis. Load step analysis of DC-DC converters is a type of circuit simulation that is used to determine how a DC-DC converter responds to changes in the load current. In TINA and TINACloud, you can also quickly simulate the circuit response to a load step. Open the following circuit. To see how the circuit responds to a step change in the load current, run transient analysis. In a few seconds, the circuit response will appear in a diagram. The simulation results show good agreement with the voltage measurements in the TS30012 datasheet. Comparison of simulation and measurement results. AC analysis. The built-in average models of DC-DC converters in TINA and TINACloud allow fast and accurate AC analysis. AC analysis is a powerful tool for designing and optimizing DC-DC converters. It provides the frequency response of the converter, which can be used to analyze its stability and performance under different conditions. Load the following circuit. Select AC analysis from the analysis menu and run AC transfer. The AC Bode diagram of the loop gain appears. Efficiency analysis. TINA and TINACloud also allow fast and accurate calculation of efficiency as a function of load current. Load the following circuit. The efficiency as functions of time and load current is calculated using a special time-dependent I-out load current. Run analysis, transient. Efficiency as a function of time. Efficiency as a function of load current, I-out. This concludes our presentation showing the analysis of all important characteristics of the Semtech TS30012 DC synchronous switching regulator. We have covered the following topics: startup transient, output voltage ripple, line step and load step analyses, AC analysis, efficiency. We hope that this information has been helpful. Thank you for your attention.
For more information, visit our website at TINACloud.com. Visit our YouTube channel to youtube.com/user/TINA Design Suite.